Hi all. So today I'll be talking about my work on the background of radio photons from primordial black holes. So I'll start by motivating this work. So as you all know about the edges 21 centimeter signal, which was found to contain an absorption feature, which was quite strong as compared to what the standard models would predict. One of the potential explanations of this signal is inclusion of an excess radio background. In the presence of this background, the signal would become more negative, as we can see from this expression. In the figure on the right hand side, shown is the edges signal by the black dash line, and a typical example of the standard model is shown by the red solid line, and we can clearly see that there is a significant mismatch between the theory and observation. In the presence of excess radio background, our signal would look like the blue solid line, and we can now clearly see that the theory and observation are in reasonable agreement. Let us now understand what this excess radio background is about. So in 2011, ARCADE2 first measured an excess radio background on the sky and was later independently confirmed by LWA in 2018. Because over here we are dealing with long wavelengths, it is customary in radio astronomy to work in terms of temperature rather than specific intensity. So in this figure, we show the temperature in log scale, and on the x-axis we have the frequency again in log scale. So the black dash line is the CMB, which is a constant at 2.73 Kelvin, and the excess radio background is shown by the dotted line, which is a straight line on this log-log plot, implying a power law relation. And the total sum of these two temperatures is shown by the solid line, which is important for the calculation of the 21 centimeter signal. The origin of this excess radio background is unknown, but clearly from the power law we can say that the origin is of highly non-thermal nature. Also, about 5% of this excess radio background can explain the depth of the edges signal. So several mechanisms have been proposed that could give rise to such an excess radio background. Here I have given a short list which is not an exhaustive one. So for example, annihilating axion-like particles could produce the photons, or the resonant conversion of the dark photons into the standard model photons, and several other examples are there which could give rise to such an excess radio background. So in this work, we are going to find if the primordial black holes could give rise to such an excess radio background. So for that, we are going to consider two types of primordial black holes. First are the evaporating ones, and then we will consider the accreting primordial black holes. I would like to digress for a moment to motivate why we consider primordial black holes. So primordial black holes are interesting dark matter candidates that have been studied for a few decades now. So primordial black holes can exist in a very broad range of masses. In our previous work, the link to which is given at the bottom, we had put constraints on the primordial black holes in mass range of 10 to the 15 to 10 to the 17 gram using the edges 21 centimeter signal, and we had found that our constraints are stronger than all other constraints in the same mass range. The figure on the right hand side is a consolidated plot showing results from previous work, and our result is shown by the red solid line. In this figure, the shaded region shows the ruled out values of FPBH, which is basically a measure of the mass of the primordial black holes relative to dark matter. So let us now understand what are the evaporating primordial black holes. So in 1970s, Hawking and others had proposed that the black holes are not really black and they emit a radiation which we know as the Hawking radiation. So this Hawking radiation is relevant for masses in between 10 to the 15 to 10 to the 17 gram. So why this is the case? Because the mass loss goes as 1 by m square. So if I consider very low masses, then these masses would have evaporated before we can observe them today. On the other hand, if I consider very heavy black holes, So the emission would be so low that they would be undetectable. And so the range comes down to this very specific one, which is 10 to the 15 to 10 to the 17 gram. Also, the emission for these black holes peaks in the range of 10 mega electron volts to 100 kilo electron volts. But we can already see that this energy range is very far from the energies that we are interested in, which is lies in the radio wave band, for which the typical energies are in the micro electron volt scale. So we are going to expect very small numbers. Let us now look at the results in a more quantitative fashion. So in this figure, the y-axis shows the specific intensity in log scale, and the x-axis is the energy, again in log scale. Also, there is a secondary y-axis which shows the specific intensity related to the CMB. So from these numbers, we can clearly see that the radio emission is going to be very small from the evaporating primordial black holes. Also, the gray shaded region over here corresponds to the the frequency band in which the ARCADE2 made their observation. And also there is a of particular interest is the energy at the wavelength of 21 centimeter shown by the black dashed line. So this blue line shows the results for the primordial black hole of mass 10 to the 17 gram, for which the emission peaks at around 1 mega electron volt. On the left of the this peak energy, the emission is power loss suppressed, and so in the band where we are interested, the emission is so low that virtually radio emission is non-existent. And so clearly we are led to conclude that the evaporating primordial black holes do not produce an appreciable radio background in order to explain the excess radio background. Let us now consider a completely different class of primordial black holes, which are the supermassive ones. So these black holes have masses of the order of 10 to the 8 solar masses, and this figure that you see is an artistic impression which shows a supermassive black hole sitting at the center and accretes matter around it. And these accreting primordial black holes are thought to produce strong electromagnetic emission in form of jets. Let us now make an estimate of the specific intensity of the jets from the accreting primordial black holes. For that, we start with the very basic relation which connects the specific intensity to the emissivity. So emissivity is defined as the emission rate per unit volume per unit energy. Note that we are summing the emissivity over a range of time where the starting point is the epoch ever since the when the photons has started propagating freely till the time of the observation, which is T naught. So emissivity in turn can be estimated as the emission from a single accreting primordial black hole times the number density of such black holes. So over here the NPBH is the number density and LR is the emission for a single black hole. Because the emission mechanism for these jets are not very well understood, we often make use of empirical relations such as the fundamental plane of black hole activity, which connects the radioluminosity to the mass of the accreting primordial black hole. So in this relation, F duty is the duty cycle, which gives us the probability for a black hole to be actively accreting at a particular time, and lambda is the Eddington ratio, which gives us the total luminosity with respect to the Eddington luminosity. This specific luminosity has a power law dependence on energy, and for synchrotron emission mechanism for these jets, this comes out to be minus 0.6. But I would like to draw your attention to this index, which is particularly interesting because if you convert this in terms of temperature units, we will see that it has a power law index of minus 2.6. So this is also the same as the one seen by the ARCADE and LWA, which makes these accreting primordial black holes an interesting candidates in order to explain the excess radio background. So let us now see our results. So I will show the specific intensity in units of temperature to make an easier comparison with the ARCADE and LWA observation. So this can be achieved by the Rayleigh's estimate, which I had also mentioned earlier. So, so firstly, the black dash line is the CMB temperature, which is of course a constant at 2.73 Kelvin. Uh, with a certain value of the lambda NFUT, we can explain the 5% limit of the arcade and LWA. So this special about this 5% is that it explains the anomalous depth in the edges signal. But leaving aside the edges signal, we can even explain the full arcade and LWA limit by readjusting these lambda NFUT parameters. So what is interesting over here that clearly that the not only the magnitude is explained, but also the slope of this radiation is explained, and this makes these accreting primordial black holes quite interesting in candidates that explain the excess radio background. So let us now conclude. So we have seen that the evaporating primordial black holes have a very low radio emission and hence cannot possibly explain the excess radio background as seen by the arcade and LWA. However, the accreting primordial black holes are very interesting candidates as they have a very strong radio emission, and these accreting primordial black holes not only explain the magnitude but also explain the power law index, which is minus 2.6. uh, for the 21 centimeter signal, we have seen how the excess radio background can elevate the tension between the observation and the theory. So thank you for listening.